In Chapter 1, I will introduce the metric system, the units of measure in the metric system, conversion factors, which are used to convert between denominations of the same unit of measure for a certain quantity. And I will also discuss some mathematical concepts that are important and will be used throughout the entire course. First, I'd like to start with a few words about what physics is in relation to nature and the world around us. And then we will move on to talk about units and so on and so forth. So physics has developed out of the efforts of men and women to explain our physical environment. And physics encompasses a large variety of phenomena. For example, planetary orbits, radio and TV waves, magnetism, lasers, optics, machinery, electronics, and so on and so forth. So physics has evolved from the observations of people of various natural phenomena. For example, historically, the first things that people noticed were the periodic motions of stars and planets across the sky. The most obvious one would be the sun and the moon. People have also noticed that objects that were thrown by hand move in a specific way and behave in a particular manner. And so all kinds of observations were made and theories were produced trying to explain these phenomena. And with the evolution of technology over the centuries, people were able to develop working theories and test them so that they can predict how nature will behave in one situation based on the results of that obtained experimental data in another situation. So based on various theories that were formed trying to explain different phenomena, predictions were possible for other phenomena that were not necessarily directly related, but similar behavior was observed. So, for example, Newton's laws are the three laws that explain how forces change the way objects move. And so these laws can be applied to something as simple as a block of wood that can slide across a wooden floor. Well, but Newton's laws are also applicable in rocketry. Fundamentally, the motion of a rocket is governed by Newton's three laws. Similarly, Maxwell's equations were equations that were derived to explain how the electromagnetic waves in nature propagate and behave. So those equations apply for all kinds of electromagnetic waves. And then in more specific example, these equations are used in telecommunications because radio and TV waves are also electromagnetic waves. So all these theories were formed, but then they had to be checked experimentally to make sure that the results of the experiment would confirm those theories. And so physics experiments involve the measurement of a variety of quantities. And so these measurements should be accurate and also reproducible. We wouldn't want to make a measurement, let's say, of an object free falling towards the ground, where the results change based on whether it's day or night, whether it's cold or hot, or whether the measurement is made on the east coast or on the west coast. If all parameters other than geographical location or the time of day were the same, then the result of the experiment should be the same. And so the first step in ensuring accuracy and reproducibility is defining the units in which the measurements are made. And so historically there have been many different measurement systems in use, mainly based on geographical location, but over time two main measurement systems have survived, and those are the metric system and the imperial system. So in the United States, the measurement system of choice is the imperial system, although for certain quantities there are units from the measurement system that are used as well. For example, for food energy content, the calorie is a unit that's used, and that's a unit from the metric system. And for liquid volume, the liter is also used along with the gallon, and the liter is a unit from the metric measurement system. So the metric system is abbreviated with SI from French, Système International, otherwise known as the metric system. And three important units in the metric system are the meter, which is a unit of length, and the abbreviation for that unit is M. The kilogram, which is a unit of mass, the abbreviation is kg. And the second, which is a unit of time, as we know, and the abbreviation is S. So each of those units is determined by a standard by which it is measured. So for example, for the meter, the standard, which is now not used anymore, used to be the length of a platinum iridium rod, like the one shown in the picture here, which is kept at specific temperature, pressure, and humidity conditions in France. And so the length of this rod is standardized to be 1 meter. The length of this rod wouldn't change over time because it's kept at specific conditions. And so if a science lab wants to make sure that they have a rod of length 1 meter, they would take their rod to France. They go to the lab which keeps the main standard, and then they will measure their rod against the standard. And that's how they will calibrate to make sure that they have a 1 meter length standard of their own. Similarly, the standard for mass is the mass of a cylinder, which is made from platinum iridium alloy. And so the mass of this cylinder is exactly 1 kilogram. And again, different labs around the world will go to the lab that keeps the standard, which is also in France. And then they will measure their standards against that standard to make sure that they are accurate. So here in this table, we have the units for length, mass, and time in the metric system, SI. As I discussed already, that's the meter, the kilogram, and the second. An outdated version of the metric system is the CGS system, which means centimeters, grams, and seconds, for which the standard for length was the centimeter, for mass the gram, and for time the second. The reason the change was made or transition to the metric system was that centimeters and grams are too small of quantities to actually make sense to measure with, while the meter and the kilogram are large enough to make more sense. And finally, in the imperial system, or the British system of units, the unit for length is the foot, for mass is the slug, and for time is the second. For the majority of the course, more than 90% of the time, we are going to deal with units in the metric system. it is possible we encounter some problems that will be with units in the imperial system, but one more time, most of the time we are going to deal with metric units. So that means that it is very important to remember what the units for length, mass, and time are in the metric system, because those units will be used to create other units for other quantities in the metric system. So mass, length, and time, and a few others, are considered to be fundamental quantities in nature. And so because of that, the units that are assigned to those fundamental quantities are also known as the base units. And so those are the base units in the metric system. One more time, that will be the meter for length, the kilogram for mass, and the second for time. So these are base units that correspond to those fundamental quantities. So these units can be combined in various ways to create the units for other quantities that are not considered fundamental in nature. For example, force, energy, velocity, acceleration, torque, momentum, and so on and so forth. As we work through various concepts in the course, we will find out that in certain situations it is important to change the units of a quantity. For example, if certain length is provided in millimeters, but the result of the calculation requires that the length units are in meters, that means that a conversion must be done from millimeters to meters before the calculation was completed. And so it is important to understand the relationships between denominations of the same of units for the same quantity in order to be able to perform conversions between those denominations. So here there is a list of relationships between units in the imperial system, those are the first three, and the metric system. So 1 foot is equal to 0.3048 meters, 1 mile is 1.609 kilometers, 1 horsepower is equal to 746 watts, and here the last relationship is within the metric system. The unit for liquid volume, which is the liter, corresponds to 10 to the negative 3 cubic meters. So what is the principle behind conversion of units? The principle basically lies behind the concept of a conversion factor. A conversion factor is the ratio of two different denominations of a unit that measure the same amount. So for example, I know that 1 meter of length is also equal to 100 centimeters of length. So I can take the ratio of 1 meter divided by 100 centimeters, and since that is the same length measured in different units, the ratio would be equal to 1. I can of course also flip that ratio to get 100 centimeters divided by 1 meter. Again, I divide the same length expressed in two different units, and so that also will be equal to 1. So those two ratios are conversion factors. Which help to convert between centimeters and meters. The first conversion factor will convert from centimeters into meters. The second conversion factor will convert from meters into centimeters. And so similar logic can be used to create conversion factors between all kinds of units, as long as a relationship like this one is known between the denominations of the unit. So one more time, a conversion factor is the ratio of the same quantity expressed in two different units, and this ratio is equal to 1. So let's do one quick example just to illustrate the use of a conversion factor. Let's convert 258 centimeters to meters. So here what I have is the original unit, centimeters, which I will also call the old unit, which I want to convert into the new unit, the meters. So in my conversion factor, I want to select it in such a way that I can cancel out the old units, the centimeters here, and have left only the new units, which are the meters. So then based on that information, the conversion factor that I will use for the conversion is this first one right here, where centimeters are in the denominator, those are the old units, and meters are in the numerator, those are the new units. So if I multiply 258 centimeters by 1, nothing changes, but instead of 1, I'm going to replace that with my conversion factor. So what I have is 258 centimeters times 1 meter divided by 100 centimeters. So I have centimeters in the numerator and denominator. So those are the old units, they will cancel out. And what's left is the new units, the meters, which is what I want for my conversion. And so what I have is 258 divided by 100, and this will be in meters. And so this is equal to 2.58 meters. So the same procedure can be applied for any kind of conversion, no matter what it is, as long as, again, similar relationship is known and a conversion factor can be created. Let's now look at this example of conversion between two units from different measurement systems. So the highest waterfall in the world is Angel Falls in Venezuela, and the total drop is 979 meters. Now let's express this drop in feet. So we know that 3.281 feet are equal to 1 meter. So therefore, to do the conversion, I make the ratio of 3.281 feet divided by 1 meter. That should be equal to 1. So then if I multiply 979 meters by 1 and replace it with 3.281 feet divided by 1 meter, the units of meters here cancel out. Here they are in the numerator, here in the denominator. What's left is the units, the new units, which is feet. And so 979 times 3.281 is equal to 3,212 feet. The metric system is convenient because it is a base 10 system, which means that the denominations of a unit of measurement are created by multiplying by some power of 10. So I want to give some examples here just to illustrate what that means. Let's, for example, look at the unit of length. So the meter is the unit of length, and 1 meter is the base unit. So from here I can multiply by different powers of 10 to achieve larger or smaller denominations of the base unit. So let's do a few multiplications with positive powers of 10 to achieve larger denominations of the meter. If I multiply 1 meter by 1,000, that becomes 1,000 meters, which is also known as 1 kilometer, and the abbreviation for that unit is km, where m is the unit of length meter and k is a prefix. And this prefix corresponds to 1,000, or also 10 to the third power. So that's a multiplication here by 10 to the third power. I can also multiply by a negative power of 10. Let's see what we get then. So if I multiply 1 meter by 10 to the negative second power, which is the same as multiplying by 0.01, that gives me 0.01 meters, which is also called a centimeter. And so the 10 to the negative second power corresponds to the prefix C, which is pronounced centi. So the abbreviation for a centimeter is just cm, centimeter. Again, the last letter here is the unit. The first letter or letters would be the prefix. So I can also multiply 1 meter by 10 to the negative third power. Let's see what we get then. So if I multiply 1 meter by 10 to the negative third power, which is the same as multiplying by 0.001, I get 0.001 meter. This is also known as 1 millimeter, or abbreviated that is 1 millimeter. The first letter is the prefix, the second letter here is the unit. And so 10 to the negative third power corresponds to the prefix milli. Similarly, I can create a smaller denomination by multiplying by 10 to the negative sixth power, which is micro, or I can make bigger denominations by multiplying by 10 to the sixth power, which is mega, 10 to the ninth power, which is giga, and so on and so forth. And this creation of denominations within the unit can be done for any quantity, not only for length, but it can be done for mass, it can be done for forces, for anything. It doesn't matter. And so that system of prefixes or power of 10 notation is very useful when very large or very small quantities are expressed with their values, because it allows to sort of shorthand write the quantity without having to deal with multiple zeros, multiple decimals behind the decimal point, and so on and so forth. And so this table here shows the main range of prefixes that's used in the metric system for various applications. So here, not specifically mentioned, and I will add it, is the base unit right here. So again, this can be meters, it can be grams, it can be kilograms, it can be meters, it can be grams, it can be liters, it can be newtons, anything. It doesn't matter what it is. And then by multiplying by powers of 10, as shown right here, that will produce larger denominations of the base unit. And so the abbreviations for the prefixes that correspond to those powers of 10 are shown in this middle column, and how these abbreviations are pronounced are shown in the first column. So the higher you go in vertical direction here, the larger the prefixes corresponds to bigger power of 10. Now I can go in the opposite direction and multiply by negative powers of 10, which then decreases the denomination. The symbols that corresponds to those powers of 10 are shown in the middle column here, and the pronunciation of those symbols is shown in the left column. And so the lower you would go with the power of 10, the smaller the denomination is. So understanding the units in calculating various problems is very important, because having the proper units selected and proper conversions done before calculation will produce the correct answer. And if you forget to convert a certain quantity or certain quantities to the correct units, then your answer will be off. And so the basic reasoning strategy for converting between units is as follows. In all calculations, you need to write down the units explicitly. So each quantity in the problem has to be written down with its value and the units explicitly. Then you would treat all units as algebraic quantities. So identical units are divided. They are eliminated algebraically. if identical units are multiplied, that will produce the same unit to the second power or the third power or whatever power is depending on the powers of those units. You would use conversion factors located on the page facing the inside cover of the textbook and be guided by the fact that multiplying or dividing an equation by a factor of 1 does not alter the equation. So one more time, a conversion factor is the ratio of the same quantity measured in two different units, and that ratio is always equal to 1. So multiplication by 1 does not change the result. So here is an example of another conversion where more than one conversion factor is necessary for the conversion. So in this example, let's express the speed limit of 65 miles per hour in terms of meters per second. So we know that 5,280 feet is 1 mile, and also we know that 1 hour has 3,600 seconds. And we know that 3.281 feet are equal to 1 meter. All right, so we start with the speed in miles per hour, 65 miles per hour, multiply by 1 2 times, and we replace those 2 ones with the conversion factors from feet to miles and from hours into seconds. All right, so miles are my old unit here in the speed limit. So therefore, in the conversion factor, I want miles to be in the denominator so they can cancel out. And then in the second conversion factor for the time, since hours are the old unit in the original speed limit, in the conversion factor, hours will be in the numerator to be able to cancel them out with the hours in the original speed limit. So hours cancel out. So now what's left is, miles are gone, hours are gone. What's left for the units would be feet and seconds. And so the new quantity will be measured in feet per second. And now multiplying 65 by 5,280 and divided by 3,600 gives me 95. So 65 miles per hour are equal to 95 feet per second. So here again, in this conversion, I use two different conversion factors together to do the conversion. So this type of conversion is known as chain link conversion, where I'm converting more than one unit to a different unit. So simultaneously here I converted the miles into feet and the hours into seconds. All right. But the question here is asking to convert 65 miles per hour in meters per second. So now I need to convert feet per second into meters per second. So this could have been done right here by just adding an extra conversion factor, but let's do it separately. So 95 feet per second, I multiply by 1, which would be represented by this conversion factor here, which converts from feet to meters. And I selected the ratio to be like so that my old units, which are feet and are present in the numerator in the speed limit here, are in the denominator in the conversion factor, so they can cancel out. So we have the feet units cancel out here and here. And so what I'm left with is 95 divided by 3.281 meters per second. So that is 29 meters per second. Finally, 65 miles per hour converts into 29 meters per second. So this is an example of a more complicated conversion where in the first step, I did a conversion of more than one unit at the same time. Again, this is known as a chain link conversion. And then in the second part of the calculation, I just did a single conversion from feet to meters. And through the course, you guys will be doing quite a few of those conversions or types of conversions where you convert more than one unit at the same time. So that is the method to do that. Another aspect of the importance of units in problem solving is dimensional analysis. What is dimensional analysis? Well, so to each fundamental quantity, such as length, mass, and time, we assign a dimension. So obviously length has dimension of length, mass has dimension of mass, time has dimension of time. So we assign those symbols for the dimensions of those quantities. And so when you look at a formula that relates certain quantities, for example, this formula right here, which relates distance, speed, and time to the second power, if you replace those with their dimensions of length, speed has dimensions of length divided by time, and time to the second power has dimensions of t squared, and you simplify that side, you find out that on the right side you have dimensions of length times time, and on the left side you have dimensions of length, which means that this relationship here is actually not accurate. Because if it were accurate, the dimensions on the left side would be equal to the dimensions on the right side. So they are not accurate. A simple example of such type of controversy would be if you were calculating the area of an object, and in two different ways, and then on one side you get the area to be, let's say, 5 meters, and then on the other side it is 5 meters squared. Clearly the dimensionality is not correct because these are not the same quantities. So that essentially is what this example shows. Here there is a different relationship between distance, speed, and time presented, and the dimensional analysis looks like so. On the left side, distance has dimensions of length, speed has dimensions of length divided by time, and obviously time has dimensions of time. So after simplification, the right side has dimensions of length. So the left side has dimensions of length, the right side has dimensions of length. Both dimensions are correct, so therefore this relationship here accurately describes the relation between distance, speed, and time. And so this sort of illustrates the importance of dimensional analysis for working with problems. You want your result to be in the proper dimensions so that you know that the problem is solved correctly. So now we will do a quick review of some basic trigonometry because we are going to need that knowledge for a variety of applications through the semester. So a lot of the problems that are specifically mechanics related in this course are going to deal with forces, accelerations, and other quantities that have direction and also magnitude. And so when that comes into play, it's important to be able to determine that direction of these quantities. And so for that purpose, we are going to use trigonometry. So in a right triangle, such as the one shown on the slide, we have a hypotenuse, and then we have two sides. One is the adjacent side to the hypotenuse, and one is the opposite side to the hypotenuse. And here they are labeled with HA for the adjacent side and HO for the opposite side. And the hypotenuse is labeled with H. So the adjacent side and the opposite side make a 90-degree angle with each other, and then the angle between the hypotenuse and the adjacent side is labeled as theta. So if I take the ratio of the opposite side to hypotenuse, that is defined as the sine of this angle theta. The ratio of the adjacent side to the hypotenuse is known as cosine of theta. And then the ratio of the opposite side to the adjacent side is known as tangent of theta. So these are just definitions. So here's an example application of the ideas of trigonometry for a right triangle. So I have a tall building with a known height, h0. And the sun is shining here so that the edge of the building produces a shadow right here, which is a distance of 67.2 meters from the base of the building. I also know that the line of the light that produces this shadow here and the base line are form an angle of 50 degrees. And so I can ask the question, what is the height of this building, H0? All right, so from my previous page, first of all, this is a right triangle geometrically. And for this right triangle, I do not know the hypotenuse, but I know the adjacent side, and I know the angle between the hypotenuse and the adjacent side. And what I'm looking for is the opposite side. So from the previous page, a function that relates the opposite side and the adjacent side is tangent of the angle. And so that's what I'm going to use. The tangent of the angle theta is equal to the ratio of the opposite side to the adjacent side. Or in other words, tangent of 50 degrees is equal to the opposite side divided by 67.2 meters. And so after rearranging the terms to solve for H0, H0 is equal to tangent of 50 times 67.2 meters, which is 80.1 meters. So this is a simple example of how using trigonometry can solve a problem that looks much more complicated than it actually is to solve. Okay, so now back to the right triangle that I discussed 2 slides ago. If I do not know the angle between the adjacent side and the hypotenuse, but I know the adjacent side, the opposite side, and the hypotenuse, then I can also write expressions for the angle itself to calculate it. Essentially, those would be the inverse functions of the functions discussed before. So, if I take the ratio of the opposite side to the hypotenuse, and from that I take inverse sine, then that's going to give me this angle theta. The same will happen if I take inverse cosine of the adjacent side divided by the hypotenuse, or if I take inverse tangent of the opposite side divided by the adjacent side. So these are 3 different ways, depending on which two or which pair of sides from this right triangle you know, to find the angle between the hypotenuse and the adjacent side. Another very important piece of geometry that will be extremely useful and we will use a lot through the course is the Pythagorean theorem. So for a right triangle with a hypotenuse h, adjacent side HA, and opposite side HO, the relationship between the length of the 3 sides is that hypotenuse to the second power is equal to the opposite side to the second power plus the adjacent side to the second power. This relationship gives us the opportunity to find any of the 3 sides when we know the other 2. This again applies only for a right triangle. In physics, there are 2 types of quantities. Quantities which can be described by a single number, and those are known as scalar quantities. So examples of such quantities would be temperature, speed, mass, pressure, energy, time. These quantities do not possess a sense of direction, only a sense of magnitude. So those are scalar quantities. But then we also have a different type of quantity, and that is a quantity that, besides the magnitude of it, it also inherently has a quality of direction. So such quantities are known as vector quantities. So vector quantities inherently have both magnitude and direction. So examples of such quantities would be velocity, force, displacement, acceleration, torque, momentum. So these have, besides their magnitude, also a sense of direction. So for example, if you're applying a force on an object, that object will be moving. How is it going to be moving? Well, it depends how are you applying the force. That is the sense of direction. If you're pushing on the object will be moving away from you. If you're pulling on the object will be moving towards you. the sense of direction here is important. So how do we represent vector quantities geometrically? Well, they are represented by an arrow. So we have a straight line, which can be to size or scaled, and the length will be equal to the magnitude of that vector quantity. For example, we have a 4-pound force vector here, and then the arrow represents the direction in which the force acts. So we have a straight line with magnitude equal to the magnitude of the vector quantity, and an arrow that points in the direction of the vector quantity. Here we have an 8-pound force, which is another straight line. It has twice the length of this first straight line, and an arrow that points in that direction. So what is the importance of vector quantities? Why are they important? Because they provide more information than scalar quantities, especially when it comes to positioning of objects as they move through space. So for example, if you tell somebody that you are driving at 60 miles per hour, this information only tells people how quickly you're going, and essentially you are providing a scalar quantity information to somebody else. You do not provide any information about the direction in which you're headed. So you're telling them your speed. But now if you say, I'm going 60 miles per hour due north, now you're providing an extra piece of information, and that is the direction in which you're going. So now you are giving them your velocity. You're giving them the speed with which you're going, that's the magnitude, and the direction in which you're going. And so, as an example here, there is a car that starts from a point in space. It's going on a straight line, and it travels a distance of 2 kilometers to this final position. Okay, so if I say that the car traveled 2 kilometers, that gives no information about, where the car went. It just says 2 kilometers of distance, that's it. But if I want to indicate the displacement of the car, then I have to include information for the direction. So how do I include information for direction? Well, I can look at the motion of this car in the context of an actual map, where I have north, east, south, and west directions. Okay, so I can align the motion of the car so that I have essentially two axes of motion. One is horizontal, that aligns with the west and east directions, and one vertical that aligns with the north and south directions. Okay, so now if I can measure the angle between the east direction and the direction in which the car is moving, and I know that the car went for 2 kilometers, then I can determine exactly where the car is with respect to the starting position. And so now this information here, length of travel plus the direction given by this angle here, is called the displacement of the car. So the displacement tells me more information than just the distance by which the car traveled. Imagine another situation. So I have a car that starts from this point right here, and then it travels to the right along a straight line and displaces between those 2 points. Let's label those points with point 1 and point 2. So the car displaces between points 1 and 2, and the displacement is a vector quantity. Let's call it A. And then the car stops here, waits for some time, and then starts moving again, and then displaces from point 2 to point 3. So that's a different displacement vector. Let's call it B. I can now calculate the total displacement of the car by simply adding the magnitudes of those two vectors with account for direction. So both of those point in the same direction. So therefore, I can just simply place the tail of the second vector, vector b, at the head of the first vector, vector a, and then add the two magnitudes to get the resultant vector of this addition, or that is the total displacement of this car. So the total displacement is from point 1 to point 3. That's a vector quantity that points to the right, and the magnitude of that vector quantity is equal to the magnitude of A plus the magnitude of B. So here, in the explanation of the process, I added a rule of how we can add some vector quantities. I said that I placed the tail of vector B at the head of vector A, and then the resultant vector was a vector that starts at the tail of A and ends at the head of B. In this particular situation, the geometry of the problem is very simple because everything happens along a straight line, but the same idea can be applied when the two vectors are not collinear. Before we go there, let's address this example in some numbers. The magnitude of displacement A is 5 meters, the magnitude of displacement B is 3 meters, the magnitude of the resultant displacement R is 8 meters, 5 plus 3. And now here is an example of a situation where the two displacements A and B are not collinear, they are not along the same line, they are not parallel to each other. They are perpendicular to each other. The same tail-to-head rule applies though. So this object starts to displace from position 1 to position 2, and the displacement vector is vector A. And then the object displaces from position 2 to position 3, which is the final position. And so the displacement vector is vector B. So how do I find the net displacement? Well, the net displacement I find by placing the tail of B at the head of A, and then the net displacement will start from the tail of A and end at the head of B. So the net displacement R is this vector here. Notice that I say starts and ends, which then also defines the direction of the net displacement. So notice something interesting here. The object displaced from position 1 to position 2, and then from position 2 to position 3. But the displacement between the starting position 1 and the final position 3 is this straight line between the two positions. It is not the sum of magnitude of A and B. This would be the distance traveled between the initial and final positions, but not the displacement. And this is a huge difference. Distance traveled is simply a scalar quantity, the length of the path taken, but the displacement in space is just the straight line difference between the final and initial positions. That's the displacement. This is the path, the length of path taken. So in general, the length of path and the displacement are not the same thing. They only can be the same thing if the motion is along a straight line, like the previous example here. So let's address the example in some numbers. So let's take the displacement, the magnitude of displacement A. So that will be from position 1 to position 2 to be 6 meters. And then the displacement from 2 to 3, from position 2 to position 3, the magnitude is 2 meters. So the question is, what's the magnitude of the resultant displacement? Since the two vectors A and B are not on a straight line, I can't just add the magnitudes of them to get the resultant displacement. But I notice that this is a right triangle, and I know two of the sides, which means I can use, let's say, Pythagorean theorem to find the third side, which is the hypotenuse here. So the Pythagorean theorem says that the hypotenuse to the second power is equal to the opposite side to the second power plus the adjacent side to the second power So to find the hypotenuse, I square root both sides, and the result is 6.32 meters. So the magnitude of the resultant displacement is 6.32 meters. I can go one step further and find the angle between the hypotenuse and the adjacent side. And since I know the opposite side and the adjacent side, I can use tangent of theta as the function of choice for this calculation. So tangent of theta is equal to 2 divided by 6. And then from here, theta is equal to inverse tangent of 2 divided by 6. So this is 18.4 degrees. So the direction of the resultant vector r is 18.4 degrees from east. So you can see how dealing with vector quantities provides a lot more information in determining positioning in space and orientations in space for objects that are in motion. Let's talk about some simple vector operations. So first, multiplication by a number. If a vector is multiplied by a number, that's going to scale the vector up or down. So if, let's say I have a vector of length 1 and multiplied by 5, then I'm going to get a vector of length 5. If I have a vector of length 10 and multiply by 0.5, then I'm going to get a vector of length 5. If I multiply a vector by -1, that is going to reverse the direction of the vector. And if I multiply a vector, let's say of length 2 by -4, that is going to produce a vector of length -8. So it scales up the vector, but it also reverses the direction. Next, vectors also abide by the commutative property, which means that if I have a vector A and add a vector B to that, I'm also going to get the same result if I first take B and add A to that. So the result will remain the same. The same applies for more than two vectors. For example, if I have vectors A and B added together, and then add vector C to that, that's going to be the same as adding vector A to the sum of B and C. Now we are ready to start learning more about vector addition in terms of the components of a vector. So far, when I talked about adding vectors, the situation was presented in a nice, specific way so that the addition can be done. For example, I had in one of the previous slides two vectors that were aligned on the same line, added together. And then the other example was two vectors that were perpendicular to each other, added together. Those are two specific examples that are easy to calculate without knowing any specifics about vector components or any other details about vectors. But what happens if I have vectors that are not specifically placed in space to form nice, arrangements so that they are easy to add? For example, so if I have two vectors A and B that are not oriented in a specific way in space that makes it easy for the addition to be performed, A and B are not perpendicular to each other, A and B are not aligned with each other on a straight line, so the addition of those two is pretty much impossible by using pure geometry methods. And the way to do the addition would require to introduce some new concepts, mainly components of a vector, to be able to do the addition of those two vectors. Okay, so here is the beginning of the procedure, so to say. I have a displacement vector, r, let's say of an automobile that's traveled certain distance in space along a straight line. I must select a coordinate system or a reference system in which I'm going to place this displacement vector so that I can measure angles from specific directions. So the most intuitive and common way to select such reference system would be the geographic directions: north, east, south, and west. And now I can replace those directions with two simple axes: a horizontal axis, which I can call the x-axis. And the x-axis, of course, has a positive and negative orientation. In this case here, we only have the positive arm of the axis shown. And then we have a vertical axis, which we will call the y-axis. And so the y-axis also has a positive and a negative arm. Here again, we only have the positive arm. All right, so those two axes make 90-degree angle between them. And now if I place the origin of this coordinate system at the beginning of the displacement vector r, I can present this vector as the sum of two vectors, one along the x-axis, which I'm going to call vector x, and one along the y-axis, which I'm going to call vector y. Vectors x and y are perpendicular to each other, and they are called the vector components, the x vector component and the y vector component of the vector r. So one more time, vector r from the rules of addition can be presented as the sum of two vectors, vector x along the x-axis and vector y along the y-axis. Vectors x and y form 90-degree angle between them. Vector x is known as the x vector component, and vector y is known as the y vector component of r. So any vector which is placed in a coordinate system as described can be presented as the sum of two mutually perpendicular vector components. So here is another example. So on the right side, we have the positive x and positive y axis. Vector A starts at the origin of that coordinate system, and then this vector can be presented as the sum of its x component vector, which is labeled as ax, and y component vector, which is labeled as ay. And the two vectors, ax and ay, are perpendicular to each other. The same representation can be achieved by sliding vector ay parallel to itself until it is overlaying the positive y-axis. And so that's what we see here on the left side. So vector A is presented as the sum of vectors ax and vector ay, ax being along the positive x-axis, ay being along the positive y-axis. So here I need to also state that any vector translated parallel to itself in space does not change, meaning the direction remains the same since it's parallel to itself, and of course it is not scaled up or down since it's only translated parallel to itself, so therefore the vector remains the same. So that's what I used to move vector ay from here to here to overlay with the y-axis. And so then, by the rules of vector addition, I can say that vector A is equal to the sum of its vector components ax and ay. Now, before I introduce the concept of scalar components of a vector, I need to introduce unit vectors. A unit vector is simply a vector with length 1. So the way I will introduce those unit vectors is very specific. I want to have a unit vector along each coordinate axis. So here are my positive arms of the x and y axis, so positive x direction, positive y direction, and then I am introducing a unit vector x hat oriented along the positive x-axis and a unit vector y hat oriented along the positive y-axis. So by the definition of a unit vector, the magnitude of x hat is equal to 1 and the magnitude of y hat is equal to 1. And the magnitude means the length of the vector. So then, if I select a different vector, let's say vector ax along the x-axis, I can present that vector ax as the magnitude of that vector ax times the unit vector along the x-axis x hat. Remember from before, any vector multiplied by a number is just scaled up or down. So if I multiply the unit vector x hat by this number ax, that will produce a vector called ax, this vector right here. And I can do a similar operation with the y-axis. So I can select a vector which I can call ay, and then vector ay is going to be equal to that number ay times y hat. So these coefficients here, ax and ay, are called the scalar components of the vectors ax and ay. So let's write this down. So ax and ay are the scalar components of the vectors ax and ay. So this quantity here, the scalar components of a vector, is extremely important in addition of vectors with random orientation in space. So here, this slide again talks about the scalar components. So it's often easier to work with the scalar components rather than the vector components. So here we have the unit vectors x hat along the positive x-axis, y hat along the positive y-axis, and the two vectors ax presented as the scalar components ax times the unit vector x hat, and the scalar component ay times the unit vector y hat. So that's the vector ax, vector component, and this is the vector component ay. So those two added together will produce this vector a, which would be somewhere here. And I'm not drawing the entire vector because I don't want to get into the writing there. So this vector a can be presented as the sum of the vector components ax and ay, as I did show you 2 slides ago. And so each vector component can be presented as a scalar component times the unit vector. And thus, the vector a can be written as ax times x hat plus ay times y hat, where ax and ay are the scalar components of a. So now this representation here is the representation of a 2-dimensional vector in scalar component and unit vector notation. So this representation here is known as unit vector notation. Now that I have a recipe of how to present any vector in space in unit vector notation like so, I can easily add two vectors that are randomly oriented in space. So here is the example. So I am adding vectors A and B, which are randomly oriented in space. I'm going to place them so that the tail of B is placed at the head of A. And so by the rules of vector addition, the resultant vector C will start at the tail of A and end at the head of B. Okay. So we know that C is equal to A plus B. However, if I only have these two vectors A and B in space, just provided with random orientations without any more information, this is as far as I can get adding those two vectors. But what about if I knew the vector components of A and B? So AX, AY, and also BX and BY. Well, if I knew that, then I can actually find what C is equal to. So what this picture here translates into is shown in figure B. The X component vector of A and B are added together, and the Y component vectors of A and B are added together. And so now here we have a nice right triangle. Even though the original vectors were placed like so, when you add them by components, it becomes equivalent to a right triangle. And so the side that lies along the x-axis, ax plus bx, will be the x component of C, and then ay plus by will be the y component of C. So vector A can be written in unit vector notation as ax times x hat plus ay times y hat. And vector B in unit vector notation can be written as bx x hat plus by y hat. And so then I can substitute in the above equality right here, C is equal to A plus B. So A is replaced with that part, B is replaced with that part. Actually, let's indicate that. And what that looks like is this. AX x hat plus AY y hat plus BX x hat plus BY y hat. Well, now I can group the terms so that the terms with the same unit vector are added together, and the terms with the other identical unit vector are added together. So that means AX x hat plus BX x hat are added together. And so x hat will factor out, and I just add the two components, the scalar components of A and B in the x direction. And the same thing happens to the y hat vector terms. So the scalar components ay and by added together multiply the y hat unit vector. And so ax plus bx is the scalar component cx of vector C. Ay plus by is the scalar component cy of vector C. Let's do one example problem of that type, adding vectors by components to illustrate the concept. So let's add vectors A, which is presented as 3 times x hat plus minus 2 times y hat, and B, which is minus 4 times x hat plus 5 times y hat. So the resultant vector C is equal to A plus B. And now I'm going to replace A and B with their unit vector representation. So that is equal to 3 times x hat plus minus 2 times y hat plus minus 4 times x hat plus 5 times y hat. So now I'm going to group the terms with the same unit vectors, like so. And this becomes 3 times x hat minus 4 times x hat plus And here we have minus 2 times y hat plus 5 times y hat. So this becomes 3 minus 4 x hat plus minus 2 plus 5 y hat. And so that becomes minus 1 x hat plus 3 y hat. All right, let's draw this vector in a two-dimensional coordinate system. Let's see where it is. So first I have the unit vectors here, x hat and y hat, just for reference. And so the x component of the resultant vector C is minus 1 x hat, which means that this is going to be in the negative x direction right here, minus 1. And then for the y component, we have plus 3 times y hat, so that means that this component will lie along the positive y-axis, 1, 2, 3 points up there. Okay, so then the resultant vector is going to be right here. That is C. So this resultant vector lies in the second quadrant of this coordinate system. Okay, so I want to also find the orientation in space. Find the orientation in space, which means what's the angle between that vector and the x-axis. All right. So I have a right triangle that's formed by the vector C itself, its y component, and its x component. So we have minus 1 and 3. In this right triangle are the adjacent side and the opposite side. And C itself is the hypotenuse. So from the trigonometry that I discussed earlier, you will remember that I can calculate a tangent of this angle theta right here. And the tangent of theta will be equal to Cx over Cy. So the adjacent to the hypotenuse. So I need to also mention that Cx here is minus 1 and Cy is 3. There you go. So now I can substitute Cx with minus 1 here and Cy with 3 here. And let's see what that looks like. So that is equal to minus 1 divided by 3. So that is minus 1/3. All right, so but I want the angle theta. So that means that I have to take inverse tangent of minus 1/3 to get what theta is equal to. So theta is equal to tan inverse of minus 1/3, and this is equal. Correction, the tangent of theta is equal to Cy divided by Cx, so let's fix that. We have Cy divided by Cx. And so then that means that here I have minus 3 divided by 1. And so then the inverse tangent will change to inverse tangent of minus 3. And when you calculate that, that is minus 71.6 degrees. So that is this angle right here. If you wanted to measure the angle from the positive x-axis, then what you would do is you're going to take 180 and you're going to add this angle to it, so that means minus 71.6 degrees. And then you are going to get that this is 108.43 degrees. So when we talk about orientation of vectors in space, the standard procedure is to find the angle with respect to the positive x-axis in counterclockwise direction. So that will be this angle here, 108.43 degrees. And because of the possibility of the resultant vector to be anywhere in the coordinate system, that's why you should draw the resultant vector to determine, when you do the calculation of the angle, where that angle is. Is it from the negative x-axis? Is it from the positive x-axis? So when you do the calculation properly, you're going to end up with the correct answer for the orientation, which again, by convention, should always be from the positive x-axis in counterclockwise direction. So this concludes the lecture on Chapter 1, which is Introduction to Metric System and some math concepts. You will practice quite a few of those during the classwork that you will do and the worksheet that I will present for you to work on.